of the rational homotopic groups of a finite dimensional complex.
So, I want to thank the organizers for a very efficiently organized conference. A lot of fun, and wish Dennis, if he comes back, happy birthday. So this whole story about which I'm going to talk begins with Dennis, begins with his construction of a minimal model, which John explained to us, which does this for space X. You have a 3-cube graded differential algebra. Isomorphic to the rational homotopy groups of X. And the homology of this animal is just equal to the homology of X with convergence. This construction, which so neatly ties the homology and the homotopy groups together in one simple algebraic object, then allows you to ask the following question, which intrigued me back when I was a graduate student. Everybody knows that the homotopy groups of a space can be arbitrary. Okay? Take any sequence of groups, you make a space with those homotopy groups.
What about doesn't pi 2 have to be abelian?
Be careful, I'll start telling Dennis modulo the obvious restrictions. And yeah, the higher ones have to be abelian. The question, which is nagging again, which and which now I have some answers for, is what are the restrictions on the homotopy groups when X is a finite, one-connected complex? So that's what I want to talk about. And
what homotopy groups arise as self-adjoint groups?
Exactly. And now, for those of you in my generation who therefore may have taken Latin in high school, the answer is omnia Gallia in tres partes divisa est. So we are talking about a space X, which I'll put up here. Yes, all of God. X is a finite dimensional CW complex. I didn't say finite, I didn't say simply connected. X is a finite dimensional CW of dimension n. Its universal cover is that. And I don't think I need any more notation. And what I want to talk about right from the moment are the ranks of the homotopy group. So I'll say the rank of pi k of x is the dimension of pi k of x tensor q for k greater or equal to 2, which, as Dennis points out, is abelian. Now, these things can be infinite. But in the case that they're the pi k is finitely generated, it's just the number of copies of z. Now, as I said, everything is in 3 parts. So there is the elliptic case. And this is defined by requiring that the sum of the ranks, k greater or equal to 2, of pi k of x, rank pi k of x, is finite. Then there's a hyperbolic case. And here, each rank pi k of x is finite, but the sum over k greater or equal to 2 of the ranks is infinite. And the third case, which I'll call the infinite case, says that some rank pi k of x is actually infinite. And it's not a very difficult theorem that for every x, exactly one of these three possibilities is true. And of course, they can all happen. I'll give you the example. This is S1 wedge Sn. This baby is Sn wedge Sn. And this baby is just Sn all by itself. And what I want to show you is that the behavior of these three spaces is pretty typical of what happens in general. So,
is there a case kind of in the middle, elliptic and hyperbolic?
no.
Does it grow very fast?
No, this is all there is. Every space is one of these three spaces. Finite dimensional, I don't care about pi 1, finite dimensional CW complex.
Well, here, I mean, but in this case, the ranks actually grow really fast.
So they do.
There was something
No.
between.
Answer is no.
Okay.
This is all there is. But I haven't told you how they grow in that case yet. Just these cases, they grow very fast. So let me tell you first about this space. And this work is 30 years old. It's joint with John Friedlander. And almost everything I don't attribute is joint with Felix and Thomas over 35 odd years. So what happens here? Well, in this case, the rank of pi k of x is plain 0 for k greater or equal to 2n. N was the dimension. So you know when they stop. Not only does it stop in 2 and above, you have Poincare duality. The Euler characteristic is greater or equal to 0. And here I can actually answer the question. If you give me a sequence of non-negative integers, a finite sequence of non-negative integers, integer 1, integer 2, integer 3, and so forth, I can tell you, it's a very simple calculation, I can tell you if those are the ranks of the homotopy groups of an elliptic space, yes or no. And not only can I, if they are the ranks of a homotopy of a space, I can tell you what its dimension is and what its Euler characteristic is, just from those ranks. And the example, more general in this example, is the any homogeneous space, compact Lie divided by a subcompact Lie. In fact, you have a free action of a compact Lie group on an elliptic space. The quotient space is elliptic. These are very nice spaces. There is a problem, a long-standing open problem for these spaces. This is a conjecture due to Bott, though I'm not sure he ever wrote it down, which is that if you have a closed manifold which is strictly positively curved, then it's elliptic. And you don't know how many people have tried to beat that one. That's very hard. All right, so much for elliptic spaces. For hyperbolic spaces, X, the first thing I noticed, I should have said it here, I know one other thing, the universal cover is finite. Well, H star of X tilde Q is finite. That's also true here.
Does the three-dimensional spherical space-form conjecture tell you that that problem is true in dimension 3?
The problem is, yes. There's no, in positively, I don't know there's a positively curved. Yeah, it's the 3. It's true in 3, it's trivial in 2, and nobody knows for 4 and better. All right, Here, it is also true that H star of the cover with rational coefficients is finite.
So you didn't assume simply connected, right?
I did not.
So what did you say about the universal cover here?
Its homology is finite.
And it put the fundamental group,
I don't care.
could be.
Fundamental group could be horrible. I don't care. Take the universal cover. Because the homotopy groups are finite, you're okay.
How are you dealing with pi 1's rank?
Take its universal cover. Forget about pi 1. Take the universal cover. All the homotopy groups of the universal cover are finite dimensional. All right? It's a finite dimensional space.
Right.
Its homology is finite.
Right.
Same thing here. Here, all the homotopy groups are.
Sorry, so what's the definition of elliptic space when it's found simply? Oh, k greater than 2. Ah, okay, I see. Thank you.
All right? Here again, the universal cover has finite homology, so I can treat x twiddle as if it were a finite complex. Now I have to introduce some language. Alpha x is going to be, it's a number which I define as follows. E to the minus alpha x is the radius of convergence of the Poincare series of the ellipse space. Of the formal power series summation dimension hk of omega x q z to the k. Formal power series has a radius of convergence. Call it e to the minus alpha x. And then, that one's easy. Next two are not. We'll let h be the dimension of h star of x with rational coefficients. And we'll introduce two numbers, which now I have to copy down. Beta x is equal to.
We don't know that's finite.
Which? You know. Yes, you do. H12, my apologies. Right. Beta x equals 40 times 2n log 2n where am I? 2 plus the log of h plus 1 plus 1 whole thing times the log of nh. And gamma x equals n log of h plus 1 plus 2n log of 2n. The amusement is that beta and gamma only depend on n and h. Well, I just wrote them down because we actually know what numbers work. And then here's the theorem, of which I am not going to sketch the proof. There are two theorems. One, for all k, the maximum of the rank of pi k of pi I of x for k plus 2 less or equal to I less or equal to k plus n. So this is an interval which is the same interval shifted by k in which you have homology in the universal cover. But shifted by any k you like, the rank is greater or equal to 1. So every such interval you find at least one non-trivial rational homotopic group. There are no gaps. And then the second theorem, which is the one where this other stuff comes in, for some k, can you see down here? Well, good. The maximum, here we go. In the middle is the maximum over k plus 2 less or equal to I less or equal to k plus n, same interval, the rank of pi I of x is less than or equal to e to the alpha x plus gamma x over k times k. This shows you the exponential growth is bounded. It's bounded by e to the alpha xk with an error term, which you can see that it's smaller than, it gets small as k gets big. And this is greater than or equal to e to the alpha x, e to the alpha x. And here I have to put minus beta x over log k times k. There I could put over k, and here I have to put over log k. So what you have is an asymptotic formula for this number. This is true for k big enough. K bigger or equal to k. So they do grow exponentially in these intervals. Not only do they grow exponentially, you have error terms on each side. This is, I believe, what the number theorists call an asymptotic formula. An asymptotic formula for the ranks. As k gets big, this gets better and better. For k bigger or equal to big K. All k bigger or equal to some.
Oh, for some capital K.
For some capital K. For some cap. Sorry. Yeah. Go far enough, and then this takes in and kicks in. That leaves me with the infinite case.
So basically, you're assuming the space is finite dimensional.
Yeah, that's it. That's all. That's all.
If you don't make that assumption, then arbitrary.
Arbitrary anything. Right. Once the space is finite dimensional, this kicks in. So now I can answer your question more precisely. Either it isn't there at all, essentially, or it grows exponentially with very precise limits on how it does.
Parabolic case.
There's no parabolic case. And that leaves this horrible case, the infinite case, where one of them is infinite. And there it is. This is a statement. Here's the theorem. For all k, the maximum for k plus 2, less or equal to I, less or equal to k, plus n, the rank, pi I of x. So in any one of these intervals, from k plus 2 to k plus n, take the maximum of the ranks, it's equal to infinite. So in each, it's like this, but now it's infinite every single time. So I am a little amazed that something like this should be true.
Well, I mean, kind of intuitively, the space is determined in n steps, and then the rest has to.
Yeah, I know. This was the best you could ever hope for. Right. But I was amazed that it turned out to be true. Amazed even more that you could put actual error terms to bound it. But you can. And that is pretty much all I can tell you about these spaces. Got a question? Yeah.
How do you see that there are no gaps in these bounds?
I mean, how did I prove it?
Does it follow from these bounds?
No. This is only for k sufficiently big, in which case it's trivial. For k big enough, this was much older theorem, but for the lower ones, this doesn't help you. This is real work to show that one, because this is for all k. This is eventual k. This is for every last one. So this is for every last one. That's for every last one. There you know exactly where you are. So.
You should know why you satisfy Poincare duality. I don't know what you're planning to explain with it.
I'm not. No, I'm going to do something else now. But I can tell you in 2 minutes why you get Poincare duality.
Looks like a manifold.
It does. In fact, I keep wondering, is it? But the answer for Poincare duality is, for this baby, is you have finitely many, in the model, very quickly, you have finitely many exterior guys, odd generators, finitely many even generators. Turn all the even generators into cycles, just forget about the differential, and take the part of the differential of the odd guys that just winds up in the polynomial part. All right? That guy is also elliptic, has finite homology. And that guy trivially satisfies Poincare duality, and now you have a spectral sequence which preserves the Poincare duality. Goes from that one to the one you started with.
By putting in more terms.
You put it doesn't change the Poincare duality.
The spectral sequences preserve Poincare duality.
This one does, yes. You have to be a little careful sometimes, but this one does. All right. So, there are...
It's always an even dimensional manifold.
Come again?
It's always an even dimensional manifold.
Which, the elliptic?
This thing which looks like a manifold, it always looks like an even dimensional.
No. Product of
It's
greater or equal to 0.
Oh, of course, the end.
Oh, since I'm being asked questions, if the Euler-Poincare characteristic happens to be positive, strictly positive, then there are no odd Betty numbers at all. And you have a polynomial algebra divided by a regular sequence. That's the only case with it. So you take 2 seconds and say that if you put Bott's conjecture with Chern's conjecture, you get an interesting consequence. Chern conjectured that if you had positive curvature, the Euler characteristic had to be positive, strictly positive. So if it's elliptic, and the Euler characteristic is strictly positive, all the odd Betty numbers vanish. Those two conjectures together imply that if you have a positively curved manifold of positive Euler characteristic, all the odd Betty numbers are 0. All right. So, yeah. Exactly. We're a product of those. So now, I want to remind you that if you want to talk about the homotopy groups of a space, you may as well talk about the homotopy groups of the loop space. It's the same thing with the degree shift by 1. And pi star, go back, h star of omega x, and now x is simply connected. H star of omega x is the universal enveloping algebra on a graded Lie algebra, and Lx is exactly equal to pi star of omega x tensor q. And that's always true for simply connected spaces. This is a theorem of Moore and Milnor-Moore. And for me, that's somehow the start of rational homotopy theory, is this fact. It tells you that these it should have told us that these homotopy groups can be computed by homological techniques because you're computing the homology, which means they ought to be accessible, and they turn out to be. Although you need your stuff to make it work. I also should say that everything I have said and everything I will say was first proved by playing around with Dennis's models over and over and over again. All right, this is rational coefficients. So now you have this Lie structure. And I will say what John didn't have time to say because Dennis asked too many questions. But if we look at the model, D, and if this index here indicates the length of the monomials, these are polynomials in V, if you take it in the generalized sense, and this is the length of the monomial. So image of D is decomposable, so it sends V into lambda 2V, the quadratic term, plus lambda 3V, plus and so forth. So this is clearly the dominant term. Although when you're dealing with a quadratic dominant term, you got a problem. It's not like a linear dominant term, which really tells you stuff. This one is much more subtle. And this D2 term, this piece D2, the quadratic term, is D2 is exactly dual to the Lie bracket. Said more fancily, lambda V with D2 is the Eilenberg-Chevrolet cochains on L. So now, what I want to describe to you next is what we know about the...
What Kevin was calling the functions on the moduli.
Yeah, well, he was doing with a much more complicated situation than I have. I just a simple, ordinary, graded Lie algebra starting in degree 1 and a finite type. But yes, it's exactly that. In any case, I want to talk about the ideals, the structure of the ideals in this space, in this Lie algebra, when I have a finite complex. See, you'd like to think, if you're really an idealistic dreamer, you'd like to think, well, what do we know about the structure of ideals in the classical case? Well, we know for a classical finite dimensional Lie algebra, it only has finitely many ideals. And if it's semi-simple, it's the direct sum of simple ideals, and they are uniquely determined. Now, there is no reason why classical Lie algebras should behave anything like LX. So I just mentioned that. But if we want to study this, we need some property of the Lie algebra, and here is the one that actually makes all that other stuff about the ranks work. Here's the main engine which drives everything. Is the following theorem. It's due to the three of us plus Leval and Jacobson. And it says this, that if we take x of ULX, some homological degree I, Q ULX. It's the cohomology of ULX, Q ULX. That this is non-zero for some I less than or equal to the category of x, which is less or equal to the dimension of x. This is the big thing. So this causes us to introduce a definition which one steals. Listernick-Schnirl. This is the Listernick-Schnirlman category. The minimal number of contractible sets minus 1 that you can cover X with. Okay. And it stimulates me to point out that what made it possible to really do things with rational homotopy theory was figuring out how to calculate the category of a space using its Sullivan model. Once you knew how to do that, then theorems just float. All right. So we have a definition here for any graded Lie algebra connected and finite type. The depth of L is the least m such that X M UL Q UL is non-zero. It's the Listernick-Schnirlman category, and it is the minimal number of open sets which are contractible in X and cover X.
So it's 2 for suspension.
1, because I subtract 1. Subtract 1. The classical definition, you don't subtract 1, but for homotopy purposes, it's better to subtract 1. You want cat of a point to be 0 to be 0. All right. So it turns out that if we just want to talk about Lie algebras of finite depth, we can actually say some things. But you'll never be able to classify all the ideals into finitely many because there are obviously infinitely many ideals in non-isomorphic integrated Lie algebra, which is infinite dimensional. So we're talking about L. It's an infinite dimensional Lie algebra. L equals L greater or equal to 1. And dimension Lk is finite for all k.
So you dispense with the elliptic case and you go into the other case. So it's infinite dimensional.
This is all about the hyperbolic case. So I'm looking at just at abstractly algebras like this for the time being.
That's why it's infinite dimensional.
That's why it's infinite dimensional, correct. Now, I say you can't do isomorphism classes, so I have to do something which is a little easier to work with. So I'm going to suppose U contained in W are graded vector spaces. Like that. And I'm going to say U is full in W. So it's more or less the same as W. If there exists lambda and Q such that I want dimension of WK to be bounded by something in U. So this is going to be less than or equal to the sum from I runs from K to K plus Q of dimension UI for K sufficiently large. So if you take U out a little bit further than W, then you control W. So you go from K to K plus Q, and then you've got enough in U. Sorry, there's a lambda here. You go from K to K plus Q. In that range, you have enough vectors in U to be bigger than W and K. Right? And then lambda's fixed. There has to exist a lambda, fixed Q. It doesn't vary. Once and for well, it isn't likely to be negative because these would all be 0 because that would be a negative number. Yeah, lambda's positive. And then suppose you have U of 0 and U of 1 contained in W. These are two graded vector spaces. I will say that U of 0 is equivalent to U of 1 if U0, U1 are both full in U of 0 plus U of 1. So either you, now that is an equivalence relation. In the case of my graded Lie algebra, I want to introduce a stricter equivalence relation. So in L, I say U of 0, U of 1 contained in L are L equivalent. And I write U of 0 is equivalent L to U of 1 if for all ideals I U of 0 intersect I is equivalent to U of 1 intersect I. And then comes the theorem. Chuck does break easily. theorem. If depth L equals m, then there are at most 2 to the m L equivalence classes of ideals. So this son of a gun only has finitely many equivalence classes. Moreover, when equality holds, that is when there are when there are exactly 2 to the m, then
Do we know what the depth is?
say,
Have you said that what the depth is?
yes, I did somewhere. But I covered it up. Is it somewhere? I'll say it again.
Oh, yeah, right. Fine.
It's the first integer where the x is non-zero.
Okay.
Then L is equivalent to L to I of 1 plus I of m, and depth I of j is equal to 1 for all j. And these are, of course, unique.
These are ideals?
These are ideals. These are ideals. And it's the only ideals up to the only equivalence classes.
When you say it's equal, I mean they don't,
It's
they don't
equivalent.
talk to each other.
It's a direct sum.
That's the algebra.
Yeah. The intersection of the Lie bracket 0.
Looks like this semi-simple.
It does, doesn't it? It looks like exactly like the classical case. Now I repeat what I said 5 minutes ago. I haven't the slightest idea why these guys should start behaving like those guys. All right. So that's what we know about the Lie structure.
So you didn't know that much about this Lie algebra. It's just infinite dimensional. Right?
And depth, finite depth.
Oh, and finite depth.
But the point being that it does then.
Because it comes from a finite dimensional space, and category is finite, and then you get some.
Then you get that the depth is finite and you're away to the races.
I see. So that's the topology part in a way.
Yeah, the way why it's something, it's not just algebra, it comes from the fact that finite complex means finite depth gives you that. So this is true for any hyperbolic, the Lie algebra of any hyperbolic space. But
The algebra which has this x non-zero.
exactly, and sometimes you play with sub-algebras which don't come from spaces which are useful. So now, I want now to come to the next grand challenge open problem.
What does that x mean? I forgot what that means.
I know how to define it.
Huh?
I don't have a geometric sense at all. It shows up when you do Poincare duality and you're using commutative cochains. Right? Yeah, it's the derived Hom of ULI of K. You can't map the scalars into ULX as a ULX. There's just no such thing. But because that would give you a point that commuted with all the.
Give you a point in the center, right?
No, you're doing left multiplication. ULX acts itself by left multiplication.
Oh, that's the universal enveloping algebra.
Yeah. Yeah. All right, here comes the problem, which I won't write down, but it's a question which has been around since forever. Does the Lie algebra in the hyperbolic case, does the Lie algebra contain a free Lie algebra on two generators? That would be really beautiful if it were true. So I want to say a little bit about what we do know about that. And the big example which we know about is if
Does C have to map into free zero by definition?
which is C.
In that x thing.
Yeah.
And think of it as Hom, then it would have to ground field in degree 0?
Ground field is always in degree 0.
Degree preserving maps.
Yeah.
It would be like
Yes.
a base point.
Yes, but it doesn't have you're looking at maps of all possible degree when you do Ext.
Right, I know.
So for example, if you happen to have a finite dimensional Lie algebra in odd degrees, so the universal enveloping algebra is an exterior algebra, then you can map to the top guy and that works. That gives you an X0. It's the only time you get an X0. So if depth L equals 1, L contains a free Lie algebra, E, such that the growth, whatever that means, of L over E is less than the growth of E. That's one.
Depth 1 still there? That's there, right?
If depth L equals 1. Only, so in the semi-simple case, I'm done. But I don't know that every Lie algebra of finite depth contains the Lie algebra of depth 1. If I did this, my problem would be answered.
So what's the quantifier? Assume depth.
If depth L equals 1, then.
Then L contains a free Lie algebra.
Yeah. Which is such that the growth of L over E is smaller than the growth of E. That is, E is much bigger. E is more than, much big. There's a little bit left, but it's small compared to E. It's a huge free Lie algebra. Yes.
More than full.
Yes. Yeah, it's more. Yeah, it's much more than full. If I could do something like this instead of full, I would have been very happy to get a better theorem. All right. That's one example of where you get a free Lie.
These all have depth 1.
What?
These all have depth 1.
Yeah, that's an example.
So they contain free.
They contain free Lies. So here, big free Lies while you're at it. So here's another example, which I'm running out of time, so I won't write it now. But if you have a manifold which is heterogeneous rather than homogeneous, by which I mean you have a submanifold codimension 1, which splits the manifold in two pieces. You have a sphere here and a sphere here, both odd, which are detected by closed one forms with support here and here. Then you get a free Lie. Just ordinary differential forms.
What do you mean detected?
You have a closed one form here and a closed one form there, which integrate over the respective spheres to 1. No, one form, odd forms. Excuse me, odd forms, yes. And
Then what?
then you get a free Lie. Those two spheres generate a free Lie algebra inside. And I won't do it now, but that's a very cute consequence of minimal models. It just falls right out. And finally, suppose you have a space X, which is written as Y union a cell. Attaching map, all right? Then you get a fibration sequence, which I will write as omega x goes to F, goes to Y, goes to X. And it is known since forever by Felix and Thoma and maybe others that you have H star of, just a sec, I do this right. You have H star of omega x, here's 0, goes by multiplication by something into H star of F, goes to Q, goes to 0. You have a short exact sequence of H star of omega x modules.
Of what? Short exact sequence of
Omega x acts on F, so this is an H star of omega x module. And this one trivial is. You get a short exact sequence of modules like this. Now, what does it mean for this sequence to split? It means that this map here is 0 on homology. That means that this splits. I claim that
map, the middle map?
the map from omega x to f. If that map splits, that map is 0 in positive degrees, tells you you get a splitting back here. I claim that is the non-generic case. The generic case is when this module is this morphism is non-trivial, so you don't get a splitting. If you don't have a splitting, this is an element of x1. So depth is 1. So you get lots and lots of examples. And I will give you one exact one which I worked out a month or so ago, because I won't do it here because there's no time, but I thought I might have. If you take the force skeleton of CP infinity cross CP infinity, that is CP2, wedge CP2, union of force cell. And if you start playing with the models and actually calculate, you can tell that the map doesn't split, and therefore you have that space is depth 1. That Lie algebra, that force skeleton is depth 1. It's just an amusing thing. So the last thing I want to tell you is the last open problem I want to mention, which is this. We know all these wonderful things about the Betti numbers of the loop space or the growth of the Lie algebra. We know all that. It has been asked for decades by Gromov and others, is it true that in the hyperbolic case, the Betti numbers of the free loop space grow exponentially? Because that would say that the number of closed geodesics also grows exponentially. And that is an open question today. The reason I say it's back to the beginning is because the first application of rational homotopy theory, aside from the notes, was the theorem that the Betti numbers weren't bounded, and therefore, except for the obvious counterexample, and therefore the number of closed geodesics was infinite. So the next question is, do the Betti numbers grow exponentially, in which case the number. It is not obvious, because bizarre things happen even in the elliptic case. But I will tell you that when you have this situation, a free Lie algebra inside the Lie algebra, whose growth is bigger than the growth of the quotient, then it's true. So we have now a large category of spaces in which we know that the free loop space, the Betti numbers grow exponentially, and most unfortunately, none of them are manifolds.
What?
None of them are manifolds.
Well, every space is a manifold.
None are closed.
Well, just double it.
Oh, then it works. There are lots of manifolds, but the technique, this thing about the cells, it never works for a manifold. When you attach the final cell, this always splits. I'm done. Thank you.
Please ask the questions.
Some people here may not know, because we're a lot older, so these things were grown on. And I mean, Gromov, who was here, and unfortunately died last year, but he and Wolfgang Meyer showed that if the Betti numbers of the free loop space grow, I mean, they're not bounded, then for every Riemannian metric, there are many periodic geodesics. And then, actually, in '67 in Berkeley, we were together, and he asked me once, "Oh, you're a topologist. What can you say about the Betti numbers of the free loop space?" And I said, "Oh, that's trivial, you know, because." And I heard loop space, so I said base loop space. You know, they're always unbounded unless it's very trivial. He said, "No, I mean free loop space." I went, "Oh, what's that?" You know. And then I looked a little bit, and I said, "Oh, God, even for the two-sphere, the free loop space is non-trivial." So that's like, in '67, everyone thought rational questions in topology were trivial, because they are for homology theories. So here's a natural question in geometry, even for the two-sphere, it's not trivial to see what the structure of that is. So it was one of the curiosities, what's going on?
It started things.
Yeah, the sort of. Yeah.
And the result was a result which Dennis proved with Michelin Viguet. That was her PhD thesis, actually. In fact, I will tell a Dennis story. So, Michelin defended that thesis at Lille, where I was at the time. I was on the committee. So he came up for the thesis defense, and we went out for lunch. A lot of other people too. And we had such a good time at lunch that we were sort of very late and very happy before we actually headed for the defense. In fact, Dennis said, why can't we just have the defense here? And the answer was, there was an army of people in the amphitheater waiting for this thing to happen. Yes.
Well, that's not much of a story, but it's okay.